So, how does physics actually shape every living thing around us? We're about to take a look at a kind of universal blueprint that connects the smallest bacteria to the most massive giants you can imagine, all through the basic laws of mechanics.
It sounds like a funny question, right? But the answer to it unlocks one of the deepest truths about biology. It turns out that life, with all its incredible variety, can't just take any shape it wants. There are rules. And these rules aren't written in DNA, they're written in the language of physics.
I mean, life operates on scales that are just absolutely mind boggling. It all starts down here, in this microscopic world of single celled organisms, where the basic challenges of life, like just moving through water, are completely alien to anything we experience. And then, from that tiny, tiny world, it stretches all the way to creatures of just immense size and complexity. A blue whale is the largest animal that has ever lived. It's a total marvel of biological engineering.
So, how can one set of physical principles govern such a huge range of designs? Well, the key thing to realize is that all this diversity isn't random. Nope. It's all guided and frankly limited by the unchangeable laws of things like fluid dynamics, elasticity, and gravity.
So, to find these rules, we really have to start looking at life through the lens of physics. We need to examine how these organisms deal with their environment and how the forces of nature basically set the menu for what's possible in their design. Now, here's where it gets really, really interesting. Life basically exists in two completely different physical worlds. See, for a tiny bacterium, the forces of viscosity are everything. Moving through water for them is like for us trying to swim through honey. It's thick, it's sticky, but for a big fish or a bird, inertia is the name of the game. Their momentum lets them just glide. So these two regimes, the viscous and the inertial, they demand totally different engineering solutions from life. This quote from the BioNumbers database just nails the spirit of what we're talking about. To really get the why of biology, you have to get quantitative. You have to connect the beautiful, complicated shapes of life to the cold, hard, unchangeable numbers of physics. Okay, so how do we actually do that? How do we turn these physical ideas into a science that can make predictions? Well, the answer is in this incredibly powerful concept called scaling laws, which are basically mechanistic rules that come straight from the physics of motion. Now, for these scaling laws to really work their magic, we have to compare apples to apples. There's this principle called geometric similarity. So think about a small trout and a giant tuna. They basically have the same body plan, just at different sizes. A trout and a giraffe, on the other hand, not so much. This is what makes these laws based on real physics, not just some random statistical pattern. And believe me, this isn't guesswork. Scientists figure out these laws through a super rigorous process. They start with the fundamental equations. We're talking the hardcore stuff, like Navier Stokes for fluid dynamics and the laws of elasticity for tissues. And they mathematically figure out how things like speed or wing beat frequency should change with size. And then, the moment of truth, they test those predictions against real data from the real world. And when they do that test, the results are, honestly, just breathtaking. The predictions from pure physics line up with the reality of the biological world with just stunning accuracy. Okay, take a look at this. The scaling laws predicts that as an animal gets more massive, its frequency of movement, like a wing beat or a stride, should go down according to a very specific mathematical rule. And what happens when you plot the data for actual animals, from tiny gnats all the way up to huge horses? They fall perfectly along that predicted line. It's amazing. And it doesn't stop there. The same thing goes for speed. Physics predicts that cruising speed should get faster as body length increases, again, following a precise formula. And whether you look at fish or birds or mammals, the real-world data confirms it. It's like a universal rule for getting around. And this is what shows you the true power of these laws. They hold up across a range that is almost impossible to imagine. 10 orders of magnitude of mass. That's a factor of 10 billion, from the smallest flying insects to the biggest whales. It's a truly universal blueprint for how to build a living thing. So this leads to a really tantalizing question. If these laws are so universal that they cover all of life today, could they also apply to life that doesn't exist anymore? The answer is a huge yes. We can actually use them to bring the giants of prehistory back to life, at least, in terms of their physics. So let's start with a real icon, Otodus megalodon. Fossil evidence tells us it was basically shaped like a modern great white shark, just, much, much bigger.
That makes it the perfect candidate for our scaling laws. Okay, so using a 4.5-meter great white as our starting point, the laws predict a megalodon that's 4 times as long. But here's the kicker. Because mass scales with the cube of length, its weight would be a staggering 58,000 kilograms, and its cruising speed, double that of a great white. We're talking 14 meters per second, which is over 31 miles per hour. Terrifying.
All right, let's get out of the water and onto land. Let me introduce you to Gigantopithecus, the largest primate we know of that ever lived. Since it's a relative of the modern gorilla, we can again assume it's got a similar shape and figure out just how powerful this thing was. The scaling laws for force are just dramatic. They predict that a punch from this giant could have generated an unbelievable 91.7 kilonewtons of force. Now, that's just a huge number, so let's try to put it in context.
So check this out. That force is more than 10 times stronger than a punch from a modern gorilla. And it's about 140 times more powerful than the force a professional human boxer can generate. It is pretty much literally off the charts. Okay, for our last example, let's look at Deinosuchus. This was a giant prehistoric crocodilian. And from its fossils, we can see it looked a whole lot like a modern alligator, just scaled up to absolutely terrifying sizes. We all know alligators have a pretty scary bite, right? But by applying these same scaling laws, we can estimate the bite force of Deinosuchus, and the result is a bone-shattering force of over 130,000 newtons. I mean, that's enough to crush just about anything that was unlucky enough to get in its way. And all of this leaves us with one last kind of mind-bending thought. The laws of physics right here on Earth gave us all the incredible life we know, past and present. But these scaling laws also account for variables like gravity. So what kind of biology might pop up on a world with different gravity or different atmosphere? The universal blueprint is there, it's just waiting for us to apply it.